So what does the inverse square law mean? Well, it means that if we have an observer that's twice as far away from a light source, then the light will appear not half as bright, but only a quarter as bright, that is 4 times as dim. We can see that in this diagram over here. When we get twice as far away from the source, then the width that the energy is going through doubles, and the height that the energy is going through doubles. So that means that we have the same amount of energy passing through an area that is 4 times bigger. What this means is that in each of these quarter parts, there is only a quarter as much energy as was going through the area as at this point here. So the energy is spreading out. Once it's traveled twice as far from the source, it'll be spread out 4 times as much. So this is going to be true not just for light waves, but for any three-dimensional wave that can spread out in all directions. Light waves are of course the ones that we're most familiar with, but it's also true for radio waves and other electromagnetic waves, as well as sound waves, which as we know spread out in all directions. We can test this by listening to a sound from different directions. Of course we can always hear it, so it must be spreading out in all directions. So let's look at an example. Suppose we have a light bulb over here. We measure its intensity at a distance of 25 centimeters to be 1.8 watts per square meter. So what's the intensity at a distance of 1 meter instead of a quarter of a meter? Well, the first thing to figure out is how many times as far away we are. So are we twice as far away or 3 times as far away, or? Well, to get this answer, of course, all we need to do is divide 1 meter by 25 centimeters. And what do we get? We get, of course, 4. We are 4 times as far away. So does this mean that the light will only be a quarter as intense? Well, no, not quite. Remember that we have an inverse square law. The intensity of light will decrease by a factor of 1/16. That means that we can figure out the intensity of the light by taking our intensity at 25 centimeters and dividing it not by 4, but by 16. As the distance from the source of a 3D wave increases, how does its intensity change? Does it increase linearly with distance, increase at a rate proportional to the distance squared, decrease linearly with distance, or decrease at a rate proportional to the distance squared? Now all of these can be written in a sort of similar way if we use mathematical equations. In this case, I will be proportional to distance. In this case, I will be proportional to the distance squared. In the third case, I will be proportional to 1 over distance. And in the last case, I will be proportional to 1 over distance squared. So this little symbol that looks a little bit like a fish is the symbol that means proportional to. That is, if we multiply the right side of the equation by a constant or a number, then we can turn the fish symbol into an equals sign. So, we can see right away that neither of these first two options are correct. How can we see that? Well, if intensity were to increase with distance, then that means the further away we go from the source, the brighter it appears. And we know for a fact that that can't be true. Otherwise we'd end up getting more energy out of the wave than what we started with. So does it decrease linearly with distance? Well, the answer is not for three-dimensional waves. It turns out that if we look at a two-dimensional wave, then yes, the intensity will decrease linearly with distance. That is, the intensity will be proportional to 1 over d. However, we're looking at a 3D wave, which behaves a bit differently, because it doesn't spread out like a circle, it spreads out like a sphere. So our answer is that it decreases at a rate proportional to the square of the distance. So D is the correct answer. The reason for this is because as we move away from the source, the sphere around it has its area increasing proportional to the distance squared. Remember, the area of a sphere is 4 pi r squared, and that's why we have an inverse square law. At a certain distance from a source of 3D waves, the intensity of the waves is given by I. Find the intensity at a distance of 3D, that is, 3 times as far away. Now, what will the inverse square law say about this? I is proportional to 1 over d squared, right? So if we set d to 3 times our original distance, then I will become, well, we can work this out, can't we? If we put a 3 at the bottom there, then this will equal 1 over 9 times 1 over d squared. So that means that our new I will be 1/9 of our original I. What if we instead decrease the distance by 1/2? So in this case, instead of getting 3 times as far away, we're getting twice as close. We know that our original I equals 1 over d squared. So what will happen when we take 1 over half of d squared? Well, if we know how to do algebra and fractions and things like that, we can see that this 2 squared is going to go from the denominator of the denominator to the numerator. If we take 1 divided by d on 2 squared, that's going to be the same as the same fraction reversed, right? So this will give us 4 on d squared. So the new intensity is 4 times greater than the original intensity. Our answer is 4I. Don't forget that if we divide a fraction, then that's the same as inverting and multiplying. And in fact, that will come in useful for part C. Part C asks what will happen if we increase the distance by 50%. That is, if our new distance is 1.5 times as far away as our original distance. So in this case, we're going to get dimmer by a factor of not 1.5, but 1.5 squared. If we take 3 over 2 and we invert to 2 over 3, and then we square, we end up with 4 over 9. So remember, the inverse square law means that to find out the change in intensity, we turn the change in distance upside down and square it. That's the inverse square law. Finally, let's do something with a decimal. 8.4d. So in this case, what we need to do is, once again, invert. So instead of 8.4, we have 1 over 8.4, and then square it. And we'll end up with some ridiculous number, 70.56. But then by making that division on a calculator, we can say that it's 1.42 times 10 to the minus 2i. The other way that we could write this, of course, is 0.0142. But given that we're all scientists now, it might be a good idea to get used to scientific notation.